Mercury, the smallest planet in our solar system, is a world of extremes. Known for swiftness, the planet races around the sun faster than any other. Its orbit is a mere 88 Earth days, making it a blur in the cosmic dance of our solar system. This tiny world, just a third of the size of Earth, holds many secrets beneath its seemingly barren surface. Despite its close proximity to the sun, Mercury is not the hottest planet thanks to its thick atmosphere. However, Mercury experiences the most extreme temperature swings in our solar system. Daytime temperatures can soar to a scorching 800 degrees Fahrenheit, hot enough to melt lead. But without a substantial atmosphere to trap heat, nighttime temperatures plummet to a frigid minus 290 degrees Fahrenheit. This extreme temperature variation is just one of the many fascinating paradoxes that make Mercury a captivating subject for astronomers. Its small size, swift orbit, and seemingly desolate landscape belie a world of hidden depths and intriguing mysteries. From its unusually large iron core to the possibility of ice hidden within its polar craters, Mercury continues to challenge our understanding of planetary formation and evolution. Mercury's surface is a testament to its long and tumultuous history. Heavily cratered and ancient, it resembles our moon in appearance. Billions of years of impacts from asteroids, comets, and other celestial debris have left their mark on this small world. The craters range in size from small, bowl-shaped depressions to vast impact basins hundreds of kilometers across. One of the most striking features on Mercury's surface is the Caloris Basin, a colossal impact crater spanning approximately 1,550 kilometers in diameter. This makes Caloris one of the largest impact basins in the entire solar system, a testament to the violent collisions that shaped the early solar system. The impact that formed Caloris was so powerful that it is believed to have had global repercussions, creating strange, hilly and grooved terrain on the opposite side of the planet. Despite its ancient surface, there is evidence of more recent geological activity on Mercury. Smooth plains, likely formed by volcanic eruptions, are interspersed among the craters. These plains suggest that Mercury was once volcanically active, reshaping its surface with lava flows. Additionally, long winding cliffs known as lobate scarps crisscross the planet's surface. These scarps are thought to be the result of Mercury's shrinking as its core cooled and contracted, causing its crust to buckle and fracture. Perhaps the most intriguing aspect of Mercury is its unusually large iron core. While the Earth has a core that takes up about 17% of its volume, Mercury's core accounts for a whopping 85%. This makes Mercury the most iron-rich planet in our solar system. The reasons for this disproportionately large core remain a mystery, but several theories have been proposed. One theory suggests that early in the solar system's history, when the planets were still forming, Mercury was much larger than it is today. A catastrophic collision with another protoplanet could have stripped away much of Mercury's outer layers, leaving behind its dense, iron-rich core. Another theory posits that the intense heat and solar wind from the nearby sun could have vaporized and blown away much of Mercury's lighter elements, leaving behind a planet dominated by iron. The presence of such a large iron core has significant implications for Mercury's magnetic field. Although it is just 1% the strength of Earth's magnetic field, Mercury's magnetic field is global, indicating that it is generated by a dynamo effect within its liquid outer core. This magnetic field, though weak, offers some protection from the solar wind, deflecting charged particles that would otherwise bombard the planet's surface. Mercury's orbit is not only swift but also highly eccentric, meaning it is not perfectly circular but rather slightly elliptical. This elliptical orbit, combined with Mercury's slow rotation on its axis, results in a unique phenomenon known as a 3-to-2 spin-orbit resonance. This means that for every 3 rotations on its axis, Mercury completes 2 orbits around the Sun. This unusual resonance has a profound effect on the planet's day-night cycle. A single day-night cycle on Mercury from sunrise to sunrise lasts a staggering 176 Earth days. This is twice as long as Mercury's orbital period, meaning that a single day on Mercury is twice as long as its year. Imagine celebrating your birthday every other sunrise. This unique spin-orbit resonance also creates a peculiar phenomenon known as double sunrises at certain locations on Mercury's surface. Due to the interplay between Mercury's rotation and its elliptical orbit, the Sun appears to rise, set, and then rise again briefly in the sky. This bizarre celestial dance adds to the intrigue of this seemingly small and insignificant planet. Section 5. The mysteries of Caloris. The Caloris Basin, with its immense size and prominent features, stands as a testament to the violent forces that shaped our early solar system. The impact that created this colossal crater is estimated to have occurred around 3.8 to 3.9 billion years ago, during a period known as the Late Heavy Bombardment. During this period, the inner solar system was subjected to a barrage of asteroids and comets, leaving scars on the surfaces of planets and moons. The impact that formed Caloris would have released an unimaginable amount of energy, melting and vaporizing rock and blasting debris into space. This debris likely contributed to the formation of Mercury's thin, tenuous atmosphere. The impact also created concentric rings of mountains and ridges that surround the basin, evidence of the shock waves that rippled through Mercury's crust. Interestingly, the opposite side of Mercury from the Caloris Basin exhibits a strange, chaotic terrain known as the Weird Terrain. This region is characterized by hills, troughs, and fractured plains, unlike anything else seen on Mercury's surface. Scientists believe that this weird terrain was formed by the convergence of seismic waves generated by the Caloris impact, focusing their energy on the opposite side of the planet. Section 6. Ice in the shadow of the sun. Despite its close proximity to the sun and scorching daytime temperatures, there is evidence to suggest that Mercury harbors ice within some of its permanently shadowed polar craters. These craters, located at Mercury's poles, are tilted such that sunlight never reaches their depths. The temperatures within these craters remain perpetually below freezing, creating a safe haven for water ice to exist. The first hints of ice on Mercury came from radar observations in the 1990s, which detected highly reflective areas within polar craters. These reflections were consistent with the presence of water ice. Subsequent observations by NASA's Messenger spacecraft confirmed the presence of water ice in these permanently shadowed regions. The origin of this ice is still debated, but it is thought to have been delivered to Mercury by comets and asteroids that impacted the planet's surface. Over billions of years, this water ice has accumulated within these cold, dark craters, protected from the sun's relentless heat. The discovery of ice on Mercury has significant implications for our understanding of the distribution of water in the solar system and the potential for life beyond Earth. Section 7. The formation of an enigma. The formation of Mercury remains a puzzle for planetary scientists. Its unusual characteristics, such as its large iron core, thin atmosphere, and the presence of ice, have sparked numerous theories about its origin. One leading theory suggests that Mercury formed closer to the Sun than its current position, and migrated inward over time. This inward migration would have exposed Mercury to the intense heat and solar wind of the early Sun. Lighter elements in Mercury's outer layers would have been vaporized and blown away by the solar wind, leaving behind a planet enriched in heavier elements like iron. This process could explain Mercury's large iron core and its thin atmosphere. Another theory proposes that Mercury formed from a giant impact between two protoplanets early in the solar system's history. This impact could have stripped away much of Mercury's outer layers, leaving behind its dense, iron-rich core. The debris from this collision could have then coalesced to form Venus, explaining the similar densities of the two planets. Studying Mercury provides valuable insights into the processes that shaped our solar system billions of years ago. Its ancient surface, heavily cratered and scarred by impacts, offers a window into the chaotic early solar system, when collisions between celestial bodies were commonplace. By analyzing the composition of Mercury's surface and its thin atmosphere, scientists can learn about the conditions that existed in the early solar nebula, the cloud of gas and dust from which our solar system formed. The presence of volatile elements like sodium and potassium in Mercury's atmosphere, for example, suggests that the planet may have formed from materials that originated farther out in the solar system. Mercury's unique 3-2 spin-orbit resonance also provides clues about the dynamical evolution of the inner solar system. The gravitational interactions between Mercury and the other inner planets, particularly Venus, are thought to have played a role in shaping Mercury's orbit and rotation over billions of years. Despite decades of telescopic observations and several successful spacecraft missions, Mercury still holds many secrets. Future missions equipped with advanced instruments are needed to further unravel the mysteries of this enigmatic planet. One key area of future research is the study of Mercury's internal structure. By measuring variations in Mercury's gravity field, scientists can gain a better understanding of the size and composition of its core, mantle, and crust. This information will help to constrain models of Mercury's formation and evolution. Another area of interest is the search for evidence of past or present volcanic activity on Mercury. By analyzing the composition of volcanic deposits and searching for signs of recent outgassing, scientists can learn more about the history of volcanism on Mercury and its role in shaping the planet's surface. The exploration of Mercury, like the exploration of any celestial body, is driven by our innate curiosity and our desire to understand the universe around us. By studying other planets, we gain a better understanding of our own planet's history, its place in the cosmos, and the processes that govern the formation and evolution of planetary systems. Mercury, with its extreme environment and unique characteristics, provides a natural laboratory for testing our theories of planetary science. By studying how Mercury's surface interacts with the solar wind, for example, we can learn more about the effects of space weathering on other airless bodies in our solar system. Moreover, the exploration of Mercury has the potential to inspire future generations of scientists, engineers, and explorers. The challenges of designing and operating spacecraft in the harsh environment near the Sun push the boundaries of our technological capabilities, leading to innovations that can benefit society in countless ways. Mercury, the smallest and swiftest planet in our solar system, is a world of contrasts and surprises. From its heavily cratered surface to its massive iron core, from its extreme temperatures to the possibility of ice hidden in its polar craters, Mercury continues to captivate our imagination and challenge our understanding of planetary science. As we continue to explore this enigmatic world, we can expect to uncover even more secrets that will shed light on the formation of our solar system and the processes that shape planets both near and far. Mercury, though small in size, holds big secrets that have the potential to revolutionize our understanding of the cosmos and our place within it.